In this lesson, we'll show how to determine the location of the centroid for a volume using the method of integration. Finding the location of the centroid or the center of gravity for a large volume is sometimes important in structural engineering. For example, finding the centroidal location of this large roof or the centroidal location of this column over here is important when we go to calculate the stress within these two materials. For applications in this lesson, though, we'll only consider bodies that have an axis of symmetry, such as this one. This body is actually formed by taking, say, this generating curve, z equaling a function of y, and rotating it around the y-axis to create the surface. We can find the centroidal location for this body, or the center of gravity or center of mass, using then a single equation. It would be this one. Because we know that the centroid, or the center of gravity or center of mass of the body, is really on the y-axis due to the symmetry, and therefore x bar and z bar would equal 0. To solve the problem then, we'll choose disk elements such as this, and do a single integration. We need to always orientate our element, though, so that it intersects the bounding curve at the arbitrary point. In this case, y over and z up. Once we've established this, then we can find our volume of the element. And of course, that's equal to pi times z squared, the area of the face here, times the thickness of the element, which is dy. Also, we need to know y tilde, and that's the coordinate location of the centroid for our element. It's located a distance over this way. Y tilde, in this case, would equal y. So using this information and then carrying out our integration by summing these disk elements from 0 all the way to the end here will give us our results. Now I'll show you a couple applications of this idea. We'll begin with this problem, where we want to locate the centroid for this paraboloid. And of course, it's defined by this bounding curve, z equaling 2y squared. In order to get the result then, we'll choose our disk element. And remember, it has to intersect the bounding curve at the arbitrary point. In other words, this coordinate distance is y, and this one is z. Now that we've located our element, we can define its volume. Pi times y squared, and then we have dz, the thickness of the element. Realizing that we're going to be summing along the z-axis here, we have to express y in terms of z, and that's done with our equation, isn't it? So let's rewrite this as pi, and here we have 0.5 z, and then, of course, dz. Next, we have to locate the centroid of our element, and that, of course, is this distance. We call it z tilde, but it happens to be equal to z, doesn't it? So therefore, we write this as z. Now, everything we need is defined. We can proceed to go ahead and apply our equation and get our result. First, we have the integration, summing from 0 all the way to 2 of z tilde, or z, and then our volume, pi times 0.5 z, and finally, dz. In the denominator, we simply write our volume, summing from 0 to 2 of pi times 0.5 z times dz. Realize that this constant and this one cancel with these down here. We then have the following. The integration up here, of course, is the integral of z squared dz, and evaluated between 0 and 2 will give us 1/3 of 2 cubed. And down here, of course, we have the integral of z dz, and that becomes 1/2 2 squared when it's evaluated. Working out the calculation here, we get our result, and it turns out to be 1.33 meters. The answer seems to make sense, too. That point is located about right here, the geometric center, or the centroid for the volume. We'll do one more problem, just to make sure you fully understand how this all works. Here we want to find the centroidal location for the frustum of this cone. And of course, the boundary is defined by this function right here. To solve the problem, the first thing to do is to set up our disk element. Here it is. It intersects the line, of course, right here at the point. Y over and z up. Now let's define our volume. That volume is equal to pi times y squared times dz. We're integrating relative to z, and therefore we have to solve this equation for y in terms of z and put it in here. When you do that, you have the following. Pi times 1/8, and here we have 12 minus 3z. And of course, all of this gets squared. And then we have our dz. Now let's define z tilde. That, of course, is the distance from here to here. It's equal to z. Now everything is set up here, and we can now apply our equation to get our result. So we'll do that next. Here we have the following. The integral from 0 to where? Well, from here all the way up to here, 0 to 2. And now z, which of course is z tilde, and then our volume, pi. And then, of course, we write 1/8. We have 12 minus 3z. We square this, of course, and then we have dz. Down here, of course, we just simply write our volume. And that's defined by an integration from 0 to 2, pi times 1/8. That's multiplied by the quantity 12 minus 3z. Of course, all this is squared here. And then we have our dz. Now that our two integrals are set up, we can go ahead and expand the polynomial up in here and also here, and carry out the integration term by term and get our result. Or you can use a pocket calculator and evaluate each numerically. Whichever way you do it, the answer turns out to be 0. The answer turns out to be 0. 0.786 meters. And that seems reasonable when you think about it. And so having completed our problem, we'll end the lesson.